Hi everyone, my name is Varun Koyyalagunta. I'm a design verification engineer at Tenstorrent, and today I'm going to be talking about using a modern build system to speed up complex hardware design. Most design and design verification engineers, we have the same loop that we run through every day, multiple times a day. We check out the latest design and dependencies. We make a change. Management then mandates that we build and run some smoke tests before pushing, and then we push that change to other users, right? This flow is seen throughout the industry, and not just our industry, throughout the software industry as well. Really, anyone writing code and sharing with others is going through this edit, compile, test loop all the time. And so it's a problem that's worth optimizing, right? And here I've shown like the tip how this cycle is typically implemented, right? Most Git is one of the most popular version control systems nowadays, and so you would do a Git pull, and if you have external dependencies, maybe a Git submodule update to get those as well. Then you edit your file with your favorite editor. Which editor you should choose is outside the scope of this presentation. And then make files are by far the most common way to build and run tests. And so maybe you have in your make file you have a target called test, and you do make test, and you can build and run your simulations. And then if you're lucky, you have a beefier computer, so maybe you can parallelize that across multiple threads with -J. And then finally, you get push at the end of it to share that with others, right? Pretty simple, pretty typical compile flow, right? But it leaves a lot on the table. Let me just go over some of the pain points that I've experienced with this flow. The Git submodule update. Say if you're working on a large design, you may have more than a few dependencies, direct dependencies, and some of those dependencies might be third parties, some of them might be from within the company, and then each of those dependencies might have more dependencies. You might end up downloading dozens upon dozens upon dozens of dependencies every time. And this is especially a big hit when you do a fresh Git clone, right? To download all these dependencies, especially if you're really only working on this one little piece of, let's say, this one little unit that doesn't require all these other dependencies, but you need to download them anyways because you don't know exactly which ones it may or may not require, so you have to download the whole world. And when you're running make, again, going back to an example of where you're only touching a small piece, make test will still build and run the whole world, right? It's on a fresh clone, it has to. It doesn't have anything pre-built. On a on a on a clone that you've already been working in, maybe you're lucky you've already built something and you did a good pull. It didn't update other files, so then you only have to rerun and rebuild and rerun one unit. And then this make can be parallelized across threads on your local machine, but can't leverage all the computer resources you might have. You might have other machines available with lots of threads that are just sitting idle. Another problem I've seen often with make is you have to do make clean often because it's hard to specify dependencies. Like say your rule depends on A, B, and C, but in your make file you only wrote A and B. Make doesn't tell you that you did something wrong. It'll just happily do its thing, and then one day you edit C and make, and then you run make, and it doesn't actually do anything, and you think everything is okay, it worked, and you push, but then later on you found out that your edit C just broke everything, right? So what happens is people become conservative and start having to do make clean often. and then that means you're back to square one. So that even every time you're touching a file that only affects one unit, you end up having to do make clean and build and run every unit every time, right? The make is a tool from the 70s that leaves a lot to be desired. And then finally, you do a git push to share that with others again, right? So since the 70s, build systems have come a long way. Bazel is a modern one that was first internally developed at Google and then open sourced later. It's seen widespread adoption by the software industry. It's used all over the place, really, for a couple reasons. It's and this is its claim to fame is that it's both fast and correct. Fast meaning, for a few reasons, it has better dependency management, and I'll go into each of these points in the following slides. But if you only want to build and test that one unit, and Bazel knows it doesn't need to download the rest of the world for that, right? It'll only download what it needs to build and run your unit. Bazel also has remote caching. That means if someone else in your company has already checked out that same SHA and run smoke, and then you check out that same SHA and run smoke, you will immediately just download the results. You don't have to run smoke again. And then it also has remote execution. If you configure Bazel, it can dispatch every piece of your build, or just the pieces you want, onto a compute farm. So allowing you to be massively more parallel and speed up your build. And Bazel also is more correct than Make, or it helps you be more correct. It will error 99% of the time when you have unspecified dependencies. I say 99% because developers can still be evil and still break out of it, but it puts you in a sandbox where it'll at least error most of the time, almost all of the time, and so you can fix up your dependencies to be correct. So how does one use Bazel? Well, the first thing is, and this is what happens day to day, is you specify a build graph. A build graph is specified is similar to in a file similar to a make file. Bazel has build.bazel files. In it has what are called rules. Each rule has inputs, outputs, and a command that tells it how to generate those outputs given those inputs, right? Pretty similar to a make file. And the build graph visualized might look something like this. Maybe you have this could be a build and simulation flow for running a smoke of a single test. Say you have a Python file that generates a system Verilog file that is then compiled into a simulation executable. And then you also have, let's say, a C file that's compiled and then run at runtime. You use that executable simulator, and then the test you compiled, and you produce a run.log too. And maybe some other information about whether the test passed or failed. Right? So you have this build graph that is specified in files, and when looked at this way, you can sort of see there's a lot how Bazel could optimize it, right? It could and also run each of these nodes in a safe manner. So I'll go into that safe manner first. So and it's called a sandbox execution inside Bazel. So what Bazel will do is each of these nodes specifies a command, or each of these lines rather specifies a command to run. And Bazel knows, for example, to generate test.elf, it needs test.c, but it doesn't need gen sv.py. When you run make and you say make test.elf, it'll run make test.elf in your source tree, and the command that it runs can easily access other files. Like it could easily access gen.sv if it wanted to. It's right there. And make doesn't warn you that this happened or anything. It'll happily just produce test.elf. What will happen in Bazel though is if test.elf, this command is run in a sandbox. A sandbox is basically independent directory. Bazel will generate a directory for every rule that it wants to run. And inside the directory, it'll populate via symlinks the dependencies that you say are dependencies. So you said test.elf only relies on test.c. So in Bazel Sandbox, it will create a directory and only have test.c underneath there. And so when the rule runs to generate test.elf, it'll run in that directory. And if it happens to try to access some other dependency, it won't be able to find it. Obviously, you can still sort of break this. Say, for example, if you wrote a really bad rule that has like hard-coded absolute paths, Bazel won't know about that, and you'll still be able to access that path. However, you can even mitigate that by using remote execution, where you could be running on a different machine entirely, where you don't even have access to those same absolute paths possibly. But even with local sandbox execution, Bazel will error on unspecified dependencies and allow you to fix it up. This allows Bazel to be correct and for you to almost never have to do a Bazel clean. Now to the points about Bazel being fast. The first point I had was dependency management. Let's say that gen.sv.py comes from a different repo. And let's say you cloned your repo and you only want to generate test.elf. So in a fresh clone, to generate test.elf, you don't need gen.sv.py. And Bazel knows that. You can rather than using git submodules to manage your dependencies, you can use Bazel to manage your dependencies. So you tell Bazel, hey, gen.sv.py comes from this link or this git repo. This is where you can download gen.sv.py, or maybe it's from a directory on your file system. That'll work as well. And then Bazel will know where to get gen.sv.py and when it needs to get gen.sv.py. So it knows to generate test.elf, it doesn't need to do that. So it won't do that. This can drastically speed up fresh checkout build times. I've seen people work around this with custom bash scripts, right? You could write a custom bash script that says, okay, I know I only want to generate or work on this part of the project, so you might write a bash script that knows, okay, I need to download these dependencies for this, and you're basically hand-holding your build system at that point. Meanwhile, Bazel just has these facilities built in for you. Another feature I mentioned was remote caching. Let's say someone has already checked out this repo, has already built sim.exe. Bazel can download that for you. Now, how does it do that? What happens is, well, you need to set up a remote cache, and then you need to point to your local, which will be a server or a server-like thing, and you point your local Bazel instance to that server on startup. And what Bazel will do is first it'll query that cache, and it'll say, hey, this user asked me to run this command given these inputs, and here, and oh, by the way, here are the checksums of each of these inputs. Have you already done this before? And the first time this happens, the remote cache will say, no, I haven't done this before. And so then Bazel will say, okay, so I will run this. I produce this sim.exe, and now I'm going to upload it to the remote cache. I'm going to say, hey, remote cache, here is sim.exe, and I generated using these commands and these input files that have these checksums. So the next time someone needs to do this, they can immediately download sim.exe. And this applies for your whole build graph, and that includes running simulations. So if smoke is part of your build graph, that means, and you have 1,000 tests, and someone else has already run those 1,000 tests on that shell, Bazel will just immediately download the run logs from each of those tests. It's all cached. It won't even require a license. It saves a lot of time. Remote execution is the final point I had for Bazel being fast. Bazel can, similarly to how you can configure a remote cache for Bazel to talk to, you can also configure a remote execution protocol, or sorry, a remote execution server for Bazel to talk to. And there's actually some free open source implementations as well as paid commercial implementations of Bazel remote execution servers. That if you're starting from scratch, you could just, and you have a few machines, you can just download one of those projects, start it up, and point your Bazel Bazel instance to that, or or your Bazel command to that, and it'll immediately start dispatching jobs to it. And the way it works is Bazel will there's an open protocol called the Remote Execution API, and Bazel will talk to the remote execution server through that protocol, and the remote execution server responds in that protocol. So that allows the remote execution to decoupled, and allows you to choose whichever remote execution implementation you're comfortable with for your setup. And this allows a lot of flexibility. Let's say you're at a company which already has a lot of resources, has had a lot of resources, and already has a legacy batch scheduler set up like LSF. All right, LSF doesn't understand this remote execution protocol. But you can, but because it's an open protocol, you can write a simple server that Bazel talks to over the protocol. So Bazel, in this example here, I've labeled LSF shim. So what will happen is Bazel will say, "Hey, do this command for me, like generate test.elf for me," and this LSF shim will say, "Okay, I'm gonna take that and translate that into a bsub command. I'm gonna submit that to LSF. LSF then does a bsub, runs that command somewhere on one of your compute nodes, and then the output is sent back to LSF shim, which then responds to Bazel with, "Hey, this is the output, right? This I created test.elf. Here it is." So because Bazel, the remote execution server, and for that matter, the remote cache server is sort of decoupled from Bazel, it allows you to be flexible with the implementation and even write your own implementation depending on your batch scheduler. All right, so that's an overview of Bazel and its features. Now I want to talk a little bit about how Bazel has helped us at Tenstorrent. At Tenstorrent, we've seen our remote execution and remote caching vastly speed up our testing times. The numbers here are gathered not from user runs, but from CI runs. If you included user runs, the numbers would be even the savings would be even greater. But we have CI runs that run whenever someone does a git push to our main branch. And if that and that CI job will run smoke, which consists of building a handful of different test benches and then running hundreds of tests split across those test benches. So if you only had 8 local threads, we configured Bazel to first run with only 8 local threads for this experiment, and the average time for that smoke was more than an hour. But if we parallelize that across 100 threads across machines, we found our execution time went down drastically, three times, to under 20 minutes. And there were some diminishing returns there. Here, if we increase the parallelism to 500 threads, it only went down to a little bit less than that. Here we have to balance, the number of machines we have and contention between users, as well as the parallelization of our build graph. So 500 or 1,000 or more threads is totally a possibility, and Bazel can totally do it. Bazel isn't the bottleneck here; it's more of our build graph and compute system. Bazel will parallelize as much as you let it. And then obviously remote caching speeds up even further. So for CI runs that have nothing to do, they will finish in a couple minutes. They will just query the cache, download all the results that have already happened. This is pretty common on, say, if you make a documentation only change. So here is a histogram of the CI smoke runs spread throughout over one typical day at Tenstorrent. This is actually from a few months back, and our project has grown significantly. So the savings are actually probably more than advertised for us now, more than this for us now. But these are the numbers I gathered a while back. So on this day, there were 71 CI runs. And like I said on the previous slide, the average run time from scratch with no caching and 100 threads is just under 20 minutes. Right? But what we see here is that typically not everything needs to be built and run. Right? Only on the very right side of the graph is only a handful of time of the day did someone touch something that required everything to be built and run. And on the very left, you see only a handful of times did someone touch something that required nothing to be run, but that still happened a couple of times. Maybe someone was making a documentation change or similar. Most of the time, it's in the middle, where someone maybe affects one test bench, and that, or possibly two if you have like a unit test bench and an integration test bench. So and that's why most of the smoke times are towards the left here in the middle. You never really because of remote caching, you hardly ever hit the worst case where you have to build and run everything. Totaled up, this is we saved more than 13 hours of CPU time. 13 hours of wall clock time rather per day due to caching. That's a lot of both resource saving, including licenses and money as a result. So my conclusion is that modern build systems that are prevalent in the software world have a lot to offer the hardware world as well. I think I've outlined some of those things and shown a use case for a popular modern build system called Bazel. I'll stop here. Thank you, everyone.